Welcome to this presentation of Limit 2019. My name is Nik Friedl. The topic of this presentation is base material assessment according to FKM guideline. On my screen you can see a shaft with shoulder under torsion load here on the right side and bending load here on the left side. And I want to run a fatigue assessment with a combined torsional bending loading situation on the shaft, which means I have a range of torque from 50 megapascal nominal stress up to 150 megapascal nominal stress here in the area with smaller diameter. And I have a plus minus 100 megapascal bending stress here in this area. The finite element analysis results you can see here have a nominal shear stress of 100 megapascal here on the smaller diameter under torsion, which is a von Mises stress of 173. And we have a bending stress of 150 megapascal, which is equal to von Mises because in this area it's a uniaxial stress state. Okay, so what are the main steps to do so with Limit? I will start the software by double clicking, and the first step is to import the finite element model. In my case, this is a Nastran model, and here we are. So the model can be manipulated mainly with the mouse. Zoom is with the scroll wheel, and to run an assessment job with Limit, we usually start here at the left side and we work our way through to the right side all the way up to jobs. So the main steps, the most important steps, are these 4 to 5 steps, or actually 5 steps up to jobs, and the other points here are not used as often. The only exception is here the help and help index, where we have lots of documents explaining and discussing different topics. Let me point or draw your attention to this one document. It's the Limit 2019 FKM course for base and welds, base material and welds. So in a few minutes I will rush through the settings for the FKM guideline, and if you are interested in further information, you can take a look at the FKM guideline, or you can take a look at this document, which gives some more details. Okay, so I have imported a finite element mesh, and the first question is, which area do we want to assess? So for base materials, I could use the complete model, all elements, especially all elements with a outer surface, which all elements that have actually one of the element surfaces on the outer surface. But in my case, I don't want to do this. I want to use only the elements here in the area of the shoulder. So I'll mark these elements and I will create a set, and I'll call this set shoulder 01. If you define your own names, please leave the numbering here at the end, the underline 01. This is important, otherwise Limit will not recognize this element set as an assessment set. Okay, The reason why I only want to focus on these elements here in the middle is that limit also writes text output for the element with the highest degree of utilization. And due to the load importing numerical fluctuations, the node with the highest stress is somewhere here where I introduced the torsional and bending loading, and I'm not interested I'm not interested in results here in this plane. I'm more interested in results here in this area. Okay, so in the first step we have defined the area which we want to assess, and following from left to right, the next point would be sensors. Sensors are used for volume meshes where we want to do weld assessments, which is not the case here. This is a base material study, so we don't need the sensors. And the next step is to define loads. Now in limit we have these three sections. In the first section we define which finite element results we want to use. Here we will derive loads from these finite element results. You always need loads in limit to run a static or a fatigue assessment. And here in spectra you can define load groups and load cycle numbers. You can run rainflow count, you can perform rainflow counting. Actually this third area is needed if we are interested in variable amplitude fatigue problems, which is not the case for this short introduction. So I will stick to the first two areas, and the first step is to define the first finite element result, which is the torsional load. So I'll call this torsion, and all I have to do is I have to define the number of the subcase, which is 1. I will not define which result file we want to access. This will be done on the job level because this is more flexible. Okay, so I have one finite element result coming from subcase 1 called torsion, and I will define a second one called a bending. And this is subcase 2. Okay, now we need a combined loading scenario. We have torsion and bending, and the torsion will have a range from 50 to 150 megapascal. So I will define a load, and I will call it combined load case 1. CLC01, for example. I will select both loads, and I need only 50% of my finite element stress, and the bending was calculated with 150 megapascal. But I only want to use 2/3. I only want to have a bending amplitude of 100 megapascal, so I'll reduce the bending stress to 0.667. Okay, so this is my first combined load case. And since I have a rotating shaft, and the bending stress results from a vertical load, such as the weight of the structure or some other forces, I need the same torsion combined with the negative bending. So I will simply copy this, and I will change the sign here in bending and call this load case 2. Okay, so this way I have the lower torsional loading combined with reversal bending, and then we will do the same for the upper value for the torque, which is 150 megapascal. So I will copy this, call it load case 3. The torsion is 1.5, and the bending is again 2/3 of the finite element result. And last but not least, the same thing with a negative bending contribution. And then we have all possible stress states covered for this combined torsional bending problem. So these 4 load cases. Now, when we launch the limit solver, the following thing will happen in combination with the FKM guideline. We have 3D solid elements, and limit will generate or create a 2D reference coordinate system tangential to the surface, and it will reduce the 3D stress tensor to a 2D surface tensor, and then it will search for the max and min stress contributions for all stress components, 2 normal stresses and 1 shear stress, and we will also calculate the gradient normal to the surface. And since we want to rule out the influence of the orientation of the reference frame used for the fatigue assessment, we combine this algorithm with a rotating critical plane approach, which means that limit will run several fatigue analysis with different reference coordinate systems, and at the end we will have the highest degree of utilization. So there's nothing else we have to do. We simply use all these 4 load cases. Okay, so we have loads, now we need setups. In limit, a setup is the combination of an element set and some kind of design code or fatigue code or assessment rule. So I will open up the setup manager and I can create a setup. I will call it FKM shoulder. And here we have different settings. In my case, this is a base material analysis. So I'll switch to base material. The assessment code is FKM. There are different other codes available, but this is FKM we want to use. Shoulder 01 is the selected set. And then here we have to define values in order to give the software all the information it needs. We have hints that can be seen once you move the cursor to the specific variable. We also have references to tables and sections in the FKM6. So we will start from the top and run through all the values here. Not all the values have to be defined manually. Some of these areas are filled out automatically once we have defined some specific settings. So the material yield stress, the nominal yield stress should be 800 megapascal, and the nominal tensile strength should be 1000 megapascal. This is a heat treatable steel. We are not using any surface hardening, so that's why we don't need any surface strength parameters. What we do need, we have to take into account technological size effects, which means that since the diameter of the shaft is much larger than the size of the specimen which was used to test the material parameters, we have to take these size effects into account. In this case, we simply need the diameter of the shaft, which is like 50 millimeters. I'll use this value here, D effective. And then we have to define which material type this is. It's a heat treatable steel, and then limit will plot all the parameters that are typical for this type of steel in order to calculate the technological size effects. Yeah, you can always change these variables manually, but these are the default values for this type of material. Okay, what else is important? Since we are looking at a fatigue problem with lots of cycles, the plasticity is not an issue, so the plastic notch factor is set to 1. Here the user can define or select a safety concept, which is the conservative one in the default setting, which means that we assume that the high stresses will occur with a very high probability, and that the consequences of failure again are high. And then the same thing for fatigue. In this case 1.5 would be the fatigue safety factor. We do need an elongation at break because this actually is the parameter that allows the distinction between brittle and ductile material behavior. In my case I have 10% elongation at break. Roughness, let's say 10 microns should do, and everything else can be used with the standard settings. If you're aware of the FKM guideline, there are some types of overloading, and F2 actually means that we will calculate the degree of utilization assuming a constant R ratio, and MS correction means that we will take the mean stress from the finite element result. We will not manually change the mean stress. And then last point, combined degree of utilization automatically in this mode limit will automatically use a reasonable sign in this combined degree of utilization formula of the FKM. So all parameters set. With apply I can close this menu. I can close the setup manager. The next step is to define a job. The solver actually supports parallel computing, and here you can define the number of CPUs. The default is 4. The limit license does not limit the number of threads you use, so on a shared memory machine you can use all the CPUs you have. Creating a job starts with hitting the create button and defining a name. FKM shoulder is the name of my job, and that's what the new job manager looks like. First impression is it looks pretty much the same as in the version 2017. Some details are different. Let's go through them, through all the parameters, the necessary ones from top to bottom. First of all, you have to define the preference, which means which finite element code you use to generate the result. In my case, it's a Nastran OP2 file, and I want to use the English version, which means that the variable names are in English, for example. The new limit 2019 has a new result format, the H5 format, which is the new standard output. If you still want to use the old Geo output, you simply have to select this to yes. Actually, they have the same information. The H5 is a bit smaller, actually has a Nastran type of internal structure, and was introduced in order to be able to introduce more information into the results for future releases. So the next thing to do is we have to define and select result files. So this is the same as in the limit 2017. Here you simply select the OP2, and the OP2 is used to gather stress results and also to define the geometry of the finite element model. Here the stress types also unchanged, code specific. So default is 2D section plane on the surface, and I think we have everything we need up here. Next step is to select a setup, move it to the selected side, and decide what kind of assessment we want to use. We have a static strength, we have fatigue strength. The FKM actually is the only code where we can run both assessments at once. I will stick to the fatigue and the simple case of fatigue against endurance limit. Now I will choose all the load cases. Limit will go through all the load cases and it will search for the most unfavorable load combinations that will lead to the highest degree of utilization in the shaft. And with OK, we can close this and we can run the job. It's possible to look at the status of the job by simply taking a view at the command window, but this is actually a very small model, and so we're already finished. And in order to post-process the results, we simply mark the line and hit the view result button. In our case, we can select. So in this case, we'll take the old geo file format. And there is actually no change to the previous versions of limit. Within the FKM, there are no changes in the procedure. So what you see here are results. The degree of utilization already includes safety values, which means that degrees of utilization below 1 are permissible. And in order to visualize this, we can set the legend, or we can limit the legend to 1.0, which means that all the magenta area is overloaded. We have actually a symmetric solution because our loading concept is a symmetric concept. And here we can take a look if the reduction to a 2D surface tensor was successful. So a value of 2 throughout the structure means that we have a 2D surface representation, which is correct. There is no yield criteria involved in the calculation of the permissible amplitude. This could be the case with low cycle numbers and variable amplitude fatigue problems. Yeah, so that's pretty much what we can get, and maybe at the end you can take a look at elements by simply doing query, and here you will get a list of the critical load cases, load case 4 and load case 1, for example, for one of these elements. If you are interested in the position with the highest degree of utilization, you can activate the toggle max value visibility, and this will give you the highest value here of 1.34. We have the setup manager also integrated in the viewer, and here you can take a look at your settings used here in or defined in limit CA. So even in the viewer you can see which values were used in order to have a better understanding of the results. Okay. Fine. So that was a short intro in base material studies with the FKM guideline. Thanks for your attention and have a nice day. Thank you.